Hi everyone, and thank you for being here. My name is Aizierjiang and I am presenting joint work with my colleague Zhangfei from the George Washington University. Our paper is called OrbitStream. In one sentence, it's a framework for streaming 360-degree video to remote operators that needs no training at all. Instead of a neural network deciding what to send, we let physics and classical control theory do the work. Over the next 15 minutes, I'd like to convince you that this simple idea is not only elegant but genuinely competitive. Here is the plan. I will first motivate the problem. Why streaming 360-degree video for teleoperation is hard and why existing solutions fall short. Then I'll walk you through the two halves of OrbitStream, a physics-inspired viewport predictor and a control-theoretic rate controller. After that, we will look at the numbers from our evaluation and I will close with what we learned and what we are headed next. So let's start with why this problem matters in the first place. Picture this scenario. A self-driving car is handling routine traffic on its own, while a human operator sits in a control center watching a live 360-degree video feed from the vehicle. Most of the time the operator just watches. But when something unexpected happens, say a pedestrian steps out where the autonomy isn't confident, the operator has to step in immediately. This is autonomous teleoperation, and emerging 5G and 6G networks are finally making it practical, not just for driving but for surgical robots and industrial inspection platforms as well. Now, for that human intervention to work, two things are non-negotiable. The video must arrive with low latency, and it must be sharp enough for real situational awareness. One important scoping note before we go on is our work is about delivering the video stream efficiently. We don't touch the robot control side at all. Here is the core inefficiency. The camera captures a full sphere, but a human wearing a head-mounted display only looks at about 15% of it at any moment. That little green wedge. Standard pipelines don't care. They ship the entire 4K projection on the order of 150 megabytes per second, most of it never seen. The voice fix is tile-based streaming. Cut the sphere into tiles and spend quality where the user is looking. But notice that this trades one problem for two coupled ones. First, you have to predict where the operator will look, and gaze is non-stationary and depends on what's in the scene. Second, you have to split your bitrate budget across tiles while the wireless channel fluctuates underneath you. Those two problems are exactly what OrbitStream addresses. Of course, adaptive bitrate streaming is a well-studied field. So what's missing? Rule-based methods like BOLA are wonderfully lightweight, but they have no idea what's in the video. A pedestrian and an empty sky are the same to them. Model predictive approaches optimize over a horizon, but they live and die. They live and die by the accuracy of their throughput forecasts. Deep reinforcement learning, pensive future, delivers high average quality, but it needs extensive offline training and gives you a black box. And 360 specific systems like flare and panel mostly extrapolate the user's recent head trajectory, which breaks down when attention jumps to something new in the scene. For safety critical teleoperation, that last DRL point really stings. When a remotely supervised vehicle is involved in an incident, regulators will ask why the system did that and how it did, especially the reasons behind it. So our goal was a framework that is training free, interpretable, and semantic aware all at once. And that brings us to our answer, the OrbitStream framework. OrbitStream marries two old, well-understood ideas. The first is physics. We treat the objects a detector finds in the scene as masses that creates gravitational potential fields, and the operators gaze as a particle being pulled by them. That's our gravitational viewport prediction, and it reaches 94.7% prediction accuracy, completely zero viewport prediction, completely zero shot in this scenario, in the viewport prediction. No training, no per user profiling. The second idea is classical control, a proportional deliberate controller with a tangent edge. Saturation keeps the playback buffer stable empirically across 3,600 Monte Carlo simulations. We rank second out of 12 algorithms, a QoE of 2.71 against BOLA-E's 2.8. And I will argue later why that trade is worth it. One honest clarification is that training free refers to the decision and control logic, which is entirely closed form. We do not use a pre-trained YOLO v5 detector upstream, but as you'll see, the control layer degrades gracefully when that detector makes mistakes. Let me quickly set up the system. The pipeline has 4 stages, a 4K 360-degree camera at 30 frames per second, an edge server that runs YOLO v5 detection and encodes the video with HAVIC into tiles, the wireless downlink, and the operator's head-mounted display. Video is cut into 2-second chunks over an 8x4 grid, 32 tiles, each available at 6 byte rates, from 1.2 up to 40.1 megabytes per second. The key modeling ingredient is what we call here the semantic mess. Every detected object gets a weight between 0 and 1 based on how vulnerable it is. Pedestrians get the full 1.0, vehicles 0.8, traffic signs 0.75, and background clutter stays below 0.2. On the network side, the buffer fills at the ratio of channel capacity to selected byte rate and drains in real time during playback. And we assume our capacity estimate is off by at most 2 megabytes per second. How do we score quality of experience? We use the standard linear model from the literature with 4 terms: video quality with logarithmic diminishing returns. That's the Weber-Fechner law. Minus penalties for stalls, for byte rate switching, and for viewport misprediction. What's specific to teleoperation is how we calibrated the weights. The stall weight is 10, which means a single 1-second freeze wipes out roughly 3 full quality tire gains. And deliberately harsh because a frozen frame means the operator is flying blind. The switching weight is the standard 0.5 to avoid flicker and operator fatigue. And the misprediction rate is 5, so that a 20% quantity gap in the region the operator is actually watching costs about as much as dropping one quality tier. The message here is, in this setting, reliability and looking at the right place matter more than raw sharpness. Now the fun part comes in, the physics. Think of visual attention as a small test particle moving on the unit sphere, and every detected object as mass that bends the landscape around it. Formally, each object contributes a potential value whose depth scales with its semantic mass, and the total potential is just the sum over objects. The equation on the left, here we have two details matter. The delta term, set to 1, is a regularizer that keeps the potential finite when the gaze gets very close to an object, and distances are computed with the Aizierjiang formula. The proper great circle distance. Because flat planar approximations gives you wrong gradients near the poles of the sphere. In the picture you can see it in action. The pedestrian with mass 1.0 digs a deeper well than the vehicle at 0.8, and the red gaze trajectory sweeps in from the corner, bends slightly around the vehicle, and settles into the pedestrian's well. That's exactly the behavior you'd want from safety-aware predictor. From that potential, we derive two things. First, a probability that each tile will be viewed. Using Boltzmann distribution, tiles in deep potential regions get exponentially more probability mass with an inverse temperature of 1/2. This distribution is what drives bandwidth allocation. Second, the central gaze trajectory itself, which we model as a stochastic differential equation. The gaze slides downhill along the potential gradient plus Brownian noise that captures spontaneous saccades, those quick, unpredictable eye jumps. Numerically, we integrate this with Euler-Maruyama and a momentum term because eyes have inertia. Momentum decay 0.8, descent rate 0.1, saccade noise 0.05, and here is a nice sanity check. If you switch the momentum and the noise off, the model collapses to pure gradient descent with a Lyapunov convergence guarantee. The noise isn't a bug. It's what lets the model keep scanning the periphery instead of locking onto one object forever. That covers where to look. Now, how much to send? We regulate the playback buffer around a 4-second target. The error between the measured buffer and that target feeds a textbook PD controller gains 0.5 and 0.2 tuned by the classical Ziegler-Nichols recipe. The interesting twist is the saturation. We pass the control signal through a tangent edge, which gives a smooth multiplier between 0 and 2, and we scale the estimated capacity by that multiplier and a 90% safety margin. with a hard cap so we never exceed estimated capacity. The intuition is simple, with like buffer running low. The tangent edge pulls the rate down so the buffer can refuel, buffer comfortable. The rate glides up toward capacity because tangent edge is smooth. We get none of the abrupt on-off switching that plagues threshold rules. The whole loop from buffer feedback to byte rate is one differentiable path you can read off this diagram. Can we say something rigorous about that loop? Yes, a standard Lyapunov argument with the squared error as the energy function. When the buffer is in deficit, the saturation guarantees the selected rate stays below 90% of estimated capacity, and that margin absorbs the bounded estimation error. So the true capacity to rate ratio and that true ratio exceeds 1. And the energy strictly decreases. When the buffer is in surplus, the hard cap drives the rate toward capacity, which bounds further growth. Together, that gives practical boundedness of the buffer around its target. The second half of the slide is how the rate budget gets spread over tiles. Proportionally to the viewing probabilities raised to the power 1.2. That exponent, being about 1, deliberately sharpens the allocation. Byte rate concentrates around the safety critical objects, and whatever is left over after quantizing to 6-level ladder is absorbed as an execution against sudden channel drops. Putting it all together, the implementation is a two-stage loop that runs once per chunk and cleanly separates perception from control. The perception stage lives on a GPU-equipped edge server, YOLO V5 small processes each frame. Detections are mapped onto the tile grid and given their masses, and everything the client needs, positions, classes, masses, fits in a metadata packet under 1 kilobyte per frame, which is nothing next to the video itself. The control stage runs on the operator's terminal and it needs no GPU at all. Update the field, propagate the gaze equation, run the PD allocation for a typical scene. Around 8 objects, 32 tiles. That's roughly 256 vectorized evaluations per step. And the whole decision costs about like 1.01 milliseconds on average. To put that in perspective, the frame budget at 30 FPS is 33 milliseconds, and wireless round trip alone are 20 to 50. And deploying somewhere new requires no retraining whatsoever. You just bring the detector weights. So that's the design. The voice question is, does it actually work? Here's how we tested it. 3,600 Monte Carlo runs in total, 300 runs for each of 12 algorithms, with randomized initial buffers and gaze perturbations. The network side uses 40 traces, real HSDPA, and 4G mobile traces averaging 6.8 megabytes per second with a standard deviation of 3.2 plus broadband, and synthetic stress tests. The Viewport site combines two public head movement datasets from Xu et al. From CVPR 2018 and from Wu et al. From MMSIS from 2017. Augmented with synthetic teleoperation trajectories, we compare against 11 baselines spanning all four families you saw earlier. For 4 MPC variants, 2 deep learning systems, 3 rule-based methods, and the 2 360 specific systems, Flare and Panel. Here is the headline result. The bars show mean QoV plus minus 1 standard deviation over the 300 runs per algorithm. Note the figures axis is on a shifted QoV scale, and in raw QoV term, BOLA-E comes first with 2.80 and OrbitStream is second at 2.71. The black bar clearly ahead of fast MPC at 1.84 and MPC-HM at 1.67, so a completely training-free closed-form method lands within about 3% of the best-tuned heuristic and beats every optimization and learning-based controller. One reading note. The equivalent bitrate we report reflect quality delivered to the Viewport that you need to know, which can exceed raw channel throughput. That's not magic. It's tile-based allocation concentrating bits exactly where the operator is looking. Average high tails. So here is the full distribution. What you should take away from these curves is the tail behavior. Aggressive methods buy their average quality with a heavier left tail, more truly bad sessions, while conservative methods keep the distribution concentrated. And under the sub-megabit bandwidth drops in 4 stressed traces, the conservative safety margins are what keep the leading methods, including ours, essentially free of stalls. Now the prediction side, which I find the most interesting table in the paper. We count a frame as a hit when the predicted Viewport overlaps the ground truth with an intersection over union of at least 1/2. Zero shot with no training and no user profiling. GVP hits 94.7%. Pure trajectory extrapolation can reach about 98.5%, but only during slow linear panning. And it degrades on non-stationary scenes, exactly where teleoperation gets dangerous. Our semantic view, by contrast, can anticipate objects that pop up in the periphery before head overturns. The ablations tell the robustness story. Mask 30% of the objects to simulate detector failures, and accuracy drops to 82.2%, a 12.5 point hit. Graceful rather than catastrophic, because the Boltzmann distribution keeps covering the periphery. Flatten all the semantic masses to 1 and you lose 4.2 points, so the vulnerability hierarchy genuinely earns its keep. Raising the inverse temperature, sharpening the attention distribution helps on stationary targets, but it inflates viewport penalties by 41% under erratic gaze. And dropping the regularizer produces numerical singularities. So every piece of the model is there for a reason. What about stability? The PD controller keeps the buffer's standard deviation at 0.42 seconds. Compare that with 1.84 seconds for passive, with a mean level of 5.85 seconds. That means sits about the 4-second target on purpose. The 90% safety margin biases the controller conservative. The minimum buffer never fell below 4.68 seconds, and we average just under 3.5 byte rate switches per run. On latency, full disclosure, here is at 1.01 milliseconds per decision. We are slower than rule-based methods which run in microseconds and slower than the MPC variants, but against a 33 millisecond frame budget, a millisecond is simply not the bottleneck. So let me address the elephant in the room. BOLA-E scored higher, 2.80 versus our 2.71. Why would you still choose OrbitStream? Because BOLA-E acts on buffer occupancy alone. It allocates the same quality to a tile containing a pedestrian as to one containing empty sky. In teleoperation, that difference can be the whole game. OrbitStream concentrates byte rate on what can hurt people. Second, auditability. Every single decision traces back to explicit closed form equations, which is precisely what post-incident review in vehicular or surgical settings demands. Try doing that with a trained policy network. And third, zero training. New city, new camera, new environment, nothing to retrain. Even our parameters mean something physical. G is saliency weighting, beta is attention sharpness, gamma is gaze inertia. You can reason about them, and you can defend them to a regulator. Let me wrap up. To summarize, OrbitStream treats viewport prediction as particle dynamics in semantic potential fields, and pairs it with a saturated PD controller. No training anywhere in the decision logic. The numbers QoV 2.71, second of 12 baselines, buffer deviation of 0.42 seconds, and 94.7% zero-shot viewport accuracy, about 1 millisecond per decision. We are equally upfront about the limitations. We are slower than microsecond level rules. We inherit whatever mistakes the upstream detector makes, and the semantic mass hierarchy is currently static rather than adapted to individual operators. Those limitations map directly onto our next steps. Learning the masses online from operator corrections, stress testing under severe detector degradation, and recasting the stability analysis in a sample data framework. The broader takeaway I'd like to leave you with: interpretable physics-based control can stay within soft real-time margins and still be competitive, and in domains where transparency is mandatory. That combination is exactly what we need. So, are there any questions? Feel free to reach out. And this is the complete 12 algorithm table. Useful talking points is mainly that we can discuss based on this table. If you'd like to dig deeper, that our equivalent viewport bitrate is 31.52 megabytes per second against BOLA-E's 37.49. So BOLA-E spends more bits for its margin, while we spend ours more selectively. Note also on how the optimization and learning methods cluster well below both of us, from fast MPC 1.84 down to FLAIR 0.83. Decision time here is per decision control latency only, and it excludes video codecs and object detection, which are common to all pipelines. Rebuffering was rare across the leading methods. And here is the full buffer table. As you can see here, two patterns worth pointing out, which is the first one is the method that at the top, buffer-based, rate-based panel FLAIR hold buffers about 9.5 seconds, which looks safe but means they are being wasteful and sluggish. Second, the volatility column, which is mentioned here, Penicil and plain MPC are the most erratic at 1.84 and 1.76 seconds, while we hold 0.42. On switching, robust MPC and BOLA-E switch least 0.92 and exactly 1. We average 3.46 and FLAIR thrashes at 12.47 switches per run. And here are the full configurations for reproducibility. Here are some of the references that we used in presenting the slides. And thanks for watching, and feel free to contact if you have any questions. Thanks.